Hello everyone. Today we'll talk about the problem length of longest subarray with most k frequency. We are given an array of integers and want to find the longest subarray, so contiguous part, where no single value within it occurs more than k times, where k is a given integer. The values in our array can be between 1 and 10 to the 9th. K can be anywhere from 1 to the number of values we are given as input. Now, I think that this problem is a good opportunity to practice a problem-solving strategy, which is based on trying to think what if one, let's say, limitation of the problem was perhaps trivialized. And in this case, there are, I think, two main ways to try to make this problem simpler. So the first way is to only care about a single interesting value. And the second one is to consider k equal to 1. Now you can pause the video and think about how you would solve both of these problems. And now we'll talk about the main idea that is used in both of them. What you may notice is that we have the following condition satisfied in both of these subproblems and indeed in the original problem. And that is the condition that whenever we have a subarray, and that subarray is okay, and we have a subarray of this subarray, then this one is also okay. Why is that? It's because our condition for the subarray to be good is tied to the frequency of values within it. And of course, the frequencies in the subarray cannot be greater than the frequencies in the larger array. And so if they are not too big in the larger array, they are also not too big in the smaller array. And you also have the contraposition of this one, such that if you have a small array, small subarray that is not good, so some frequency is greater than k, then any larger subarray, to which this small one is their subarray, also has to be bad. And whenever you have this situation, what you can use is the sliding window technique or the two-pointer technique. So you'll be considering, for instance, every right end. So you will be trying to end after the first element, the second element, third element, and so on. And consider how far to the left you can push the left end. So the left end will start at the beginning, and whenever it is necessary to push it, so whenever the current subarray is bad, we'll push the left end until it becomes good again. Okay, so what information do we need to keep in order to solve our two simpler subproblems? First of all, for subproblem 1, where we care only about one value, then we need to keep its count. Its count is at the beginning 0. Whenever we push the right end and encounter v, we increase this count. Whenever this count becomes too big, we have to push the left end forward until we encounter v, and then we decrease the count. And whenever we stop pushing the left pointer, then we can update our result with the maximum of the previous result and the length of our current segment. And for the second subproblem, where k is equal to 1, we can remember if we have seen a given element already. And so whenever we try to add a new element, if it was not seen before, we just remember that we now see it. And if it was seen, then we have to push the left end forward until we see that element again from the left. And then we know that, okay, now everything is fine. And you can, of course, combine those two ideas now to solve the main problem. So normally we would use either an array to hold the counts for our numbers, and since these numbers are quite big, an array is not feasible, but we can also just use a map. So we'll use map from value to count. Okay, so let's see this in code. We'll be using an unordered map. You could also use a map. So if somebody were to ask you about the complexity, then of course unordered map, you can say that it's constant time. Although with some adversarial examples it can be much slower than a regular map that is based on balanced binary search trees, so it can even have linear time operations, I think. But we are using an ordered map since it's typically what you'll be asked to do. And we'll simply maintain the left end and the right end of our current subarray, which is I and j. Whenever we see another value, when we push j forward, we increase its count. And now either everything is fine, and the only thing that could have gone wrong now is that the count of this very value is too big. So it's greater than k. Well, it would have to be k plus 1. We can just see if it's greater than k. And now we'll push the left end forward until everything becomes fine. And along the way you have to remember, of course, to decrease the count of the value that we are now throwing away from our subarray. And so we'll be doing this until left v actually turns out to be the same as the value that we've seen on position j. And then we take the length of our current subarray, which is j minus I, in this case plus 1, and our result becomes the maximum of what it was previously and this length. And of course, after all this is said and done, we can return the result.